Okay, so today our big goal is to talk about motion and to actually describe motion using vectors. Now, one thing that's different that we introduced last day, we called it vector-valued functions. As I'm moving around space, I can't draw this. I can conceptualize this, but I can't draw this. And there's no function, there's no formula, there's no f of x, there's nothing that can describe motion. So what some genius figured out along the way, and I'm serious, is saying, hey, what if we consider every point on the space curve the terminal point of a vector? Then if we describe the vector in 3D, we are also simultaneously describing the space curve. Now, it's always a little confusing because a point in space is not a vector. But the terminal point of a vector is a point in space. And that's where we can go hand in hand. So by describing it this way, not only can I easily describe three-dimensional motion, I only have one independent variable, which makes the calculus really, really simple. Okay? I don't have to worry about derivatives of all sorts of different crazy things. So now, if I'm describing a curve this way, now, when I write that, you're never actually going to see an x, y, or a z. You just know that the first component refers to the x. You're going to see functions of t in each position, but the first one's the x component, the second one the y, third one the z. Then we define dr dt, and we call that v of t, and of course that would simply be dx dt, dy dt, dz dt. And then lastly, and again, I'm showing you the formal notation. It looks just like function notation. I just put a cap on that vector to make sure we understand that is a vector. And it's the third one that we really want to concentrate on the next couple of days. That's the most complicated of the bunch, and there's a lot of information there. But my position vector, remember position, think of position, if every point is the terminal point of a vector, then position really is described by distance. Literally, how far am I from the origin at any given time, okay? So therefore, if I think of t as time, then this is literally distance per time. That's why it's the velocity vector. In everyday language, we interchange speed and velocity. Is that correct? I mean, we say it all the time. When people talk, people don't say velocity. So how fast did you drive today? Oh, I got a velocity ticket. A velocity-ing ticket. Now you probably got a speeding ticket, right? we use them interchangeably because we're not talking vectors in real life. We're sort of the context that the direction I'm going is, how fast. But velocity is a vector because it refers to direction, not just magnitude. Oh, how fast were you going in that direction? But I can say that in words. The magnitude of the velocity vector is the speed, just so we understand. So the magnitude of the velocity vector is where the units would come from. And then the magnitude of the acceleration vector obviously would have acceleration units. But we don't usually refer to it that way. So these two things here have everything to do with motion. So I'm going to give you a simple example. All right. This is one of my personal favorites. Okay, we talked about this one the other day. Remember, this is a helix. I love this one here because I just drove this one recently. This is what it looks like. Okay. I use this example every semester because it's as valid as it gets. How many have ever been to the San Jose airport? So I spent a lot of time in Monterey, and I was in Santa Cruz this last weekend for a wedding. We fly into San Jose, rent a car. Have anybody ever rented a car there? It is insane. So you get your car on the 7th floor, and then when you're leaving, it's a Helix that is absurdly tight. I mean, like literally as wide as this room. And you're driving 7 floors like this. And it is hysterical. By the way, I don't ever like following somebody. I want to be the front person. Because when I follow somebody, the same thing happens every time. They've already crashed their car. Because people will drive like this and realize that they're driving right into the wall because it's so tight. When you drive, you actually have to turn your head completely sideways to know where you're going because the circle is so tight. You can't back up, there's not enough room, and I've seen people get in trouble all the time. But the point being, it's a helix. So if I'm standing on top of the z-axis and I'm looking down and I close one eye, I see a circle. I'm just going around in circles, but it's spiraling down. So I want to talk about not only your velocity, but your acceleration at every point on this, so we kind of have a picture. So we're going to do this one in a moment. I want to start with the circle, though, because this just the two-dimensional circle, then I'm going to go to the helix, because then that will help explain things. Because we're going to see some phenomena here that you may not have seen coming. Not everything's common sense. After the fact, you'll say, oh yeah, that makes perfect sense to me. But while we're doing it, it's not often the case. So let's start with a two-dimensional problem. But I'll do a simple A cos t, actually not A, sorry. I'm going to use A for acceleration. How about K? K cos t, K sine t. All right. Okay. What does this look like? Okay. At the terminal point, K cos t, K sine t, right? I have this vector. And this will describe circular motion. How do I know it will describe circular motion? Because this is the parameterization of a circle centered at the origin of radius k. And we know that even if I didn't know anything about vectors. So when t is 0, I have this vector. When t is pi over 2, I have this vector, and so on and so on and so on. Okay, so the first thing I want to look at is then, what is v of t? Help me out. What's v of t?
Negative k sine t.
Negative k sine t.
K cos t.
K cos t. Good. So if this was this guy, then that guy right there actually is that guy. And they would have a right angle there. How do I know that? Because if I do the dot product between these two, I'm going to get 0, aren't I? For, let's say t is a first quadrant angle right now. If t is pick an angle in the first quadrant, then this vector is clearly in the first quadrant. Oh, but because of that negative, now this vector is clearly in the second quadrant. That's why I know it looks like this. Another way of thinking about it is if I attach that vector here, it looks like this, doesn't it? So the velocity vector in space, what is it? As you're moving through space, we're on a circle, that makes it easy. But as I'm moving through space, the velocity vector is the direction you would slide when you hit the banana peel. That's the formal physics explanation. By the way, there's no exception. That's absolutely what it is. So as I'm moving around and I hit the banana peel, which way do I slide? In the direction of the velocity vector. That's it. Whether I'm in 2 dimensions or in 3. So as I'm moving around, I'm swinging the yo-yo as fast as I can and I let go of the yo-yo. One of my favorite things to do is ask little kids. If I'm swinging the yo-yo and I let go, what will it do? Well, it'll do a big circle in the air and it'll eventually hit the ground. Is that true? No, it'll fly off linearly, won't it? So when you hit the slick spot, you don't slide in a curve. You slide on a line, and you slide in the direction of the velocity vector. So the velocity vector is the direction I would slide, not necessarily the direction I'm going. Ooh, all right? Now thirdly, the acceleration vector. Anybody? I'm differentiating this one.
Negative k cos t. Negative k sine t.
Well, that's k cos t, then that means it's exactly 180 degrees in the other direction, isn't it? So another way of thinking about that, remember, I'm describing the motion. I'm on the rim of the circle. So I really want to start here. So my velocity vector is going this way, and at this point, what's my acceleration vector actually doing? Actually doing that. Oh, that's interesting. At every point on the circle, the acceleration vector from that point is pointing directly at the origin. Interesting, at the very least. Do you agree? It's interesting. The acceleration vector is pointed exactly in the opposite direction of my motion. That means I'm accelerating towards the center of the circle. Anybody ever have chemistry? High school or college chemistry? You know, you're putting stuff together, you want to make a precipitate, right? So you want it to separate, so what do? You put it in this little thing and it's spinning it around. What's that thing called?
Centrifuge?
A centrifuge. You put it in a centrifuge and then you spin it around and eventually, it separates. Okay? Sometimes if you're having blood taken, they'll do this with the blood and they want to separate it, the platelets and things like that. So what does that mean? As I'm doing this spinning, that means everything on the outside of this centrifuge is actually accelerating in which direction? Towards the center. Because if it wasn't going towards the center, it would actually fly off and break and it'd have a real big mess in my hands. Well, that's an interesting concept. Except that the things are being pushed outwards. I mean, shouldn't it be that the acceleration is going the other way? Doesn't it seem like it should be? But they're moving towards the center. But they're also, Now, when I was a kid, I don't remember how old I was. I might have been, I think I was a teenager. My family took a trip to, I'm from Northern California. We took a trip to Southern California and we went through Knott's Berry Farm, I remember at one point. All I remember about it was the chicken dinner. That was like legendary. And I remember that there's something called a fun house. Everybody know what a fun house is? They're not really all that fun. The distorted mirrors and all this, but there was this one room, and I don't know why I agreed to do this. I don't do well with things that spin. In general, I don't spin. I avoid things that spin at all costs. And I'm standing in a room. I remember there's this huge, gigantic human next to me. I'm pretty sure it was, Sir Gregor from Game of Thrones. I'm not sure though. And the room starts to spin. And it starts to spin faster. Anybody ever been in that evil room? Oh God, I don't know what person conceived of this. And I'm pinned against the wall. And after a couple moments, I noticed there was no floor. The floor drops out. And you're spinning, you're pinned against the wall, but I'm a little person, and the person next to me who's a huge person is also pinned against the wall. He's not falling down. Very interesting. And then eventually it slows down and the floor comes back. I'm describing this. I want to talk about the physics of what I just described. Now, you said you've been in that? Anybody else ever seen? Anybody ever heard of this? I don't know what this is called, but it's just pure evil. I was dizzy and probably throwing up for the next couple hours. Disorientation, but I still remember the spinning and the big guy not falling. At what point does the floor fall? If it fell too early, we'd all fall down with it. Now, there's two forces going on. Two. There's the force. Remember, what is force? Physics people? Mass times acceleration. Force vector is a scalar multiple of your acceleration. Mass is a scalar. So the vector of force and the vector of acceleration are the same vectors, only differing by a constant multiple. So if your mass was 1 unit, then your force and your acceleration are actually the same thing, aren't they? In terms of magnitudes. So the acceleration this way, there's a particular force, but I'm also pushed out this way. You called it a centrifuge. This is called the centrifugal force because you're accelerating towards the center. But you're also being pushed back. There's another term that sounds very similar. Almost every human being gets them wrong because they only think of the one word, not two. What's the other one called? Centripetal. Centripetal and centrifugal in the opposite directions. So think of a centrifuge. Everything has to be accelerating towards the center, otherwise it wouldn't work, but things are being pushed away. So you have a centrifugal force and a centripetal force, and one of Newton's laws says, for every action... Yeah, I really don't like the wording. It actually, that's really bad wording. First of all, the word equal can only apply to numerical values. Reactions aren't numerical values. So it's for every, basically for every force, there is a force of equal magnitude in the opposite direction. That is a better way to say it. But we just remember the real quick and dirty way of saying it. What is an equal and opposite reaction? Well, a force in the opposite direction of the same magnitude. That's pretty much what it's saying. Oh, okay. So that explains a lot of different things. You know, when I'm hitting the punching bag and depositing on it, why does it feel like the punching bag's hitting back? Because it is. I'm absorbing all this energy in reverse at the same time. So that explains a lot of what's going on here. I'm accelerating towards the center, I'm being pushed out. At what point does the floor fall? Remember, you're moving, I'm moving sideways. Gravity is something with gravity somewhere. What is gravity?
Acceleration.
It's an acceleration. Gravity is an acceleration. What is your weight? Mass times acceleration?
Due to gravity.
Mass times gravity, yeah. Mass times gravity. So in other words, your weight is the mass times acceleration due to gravity. So that is a very specific force, isn't it? When does the floor drop out? When the centrifugal force has the same magnitude as your weight. When there's the same amount of force pushing you against the wall as there is, it's actually that simple. If it was 1 instant too soon, you'd slide down, and after the fact, it doesn't matter. You're going to stay pinned forever and just, feel the G-forces and all that. Isn't that crazy? It's kind of cool. So the floor drops out. I have to be going fast, right? The numerical value of that acceleration, I'll make it simpler. The acceleration, numerically, the acceleration from the spin, the moment it equals the acceleration due to gravity. Because your mass is the same, whether you're in the centrifuge or whether you're being pushed down. It's the accelerations. When they are the same magnitude, that's when they drop to the floor. That's why it didn't matter how big the guy next to me was. Doesn't matter. He's under the same gravitational, pull that I am. Okay? So that explains some of what's going on here. So now as I'm turning, and I asked this question the other day, and almost no hands went up. No one here rides a bicycle or a motorcycle ever? Okay, so let's suppose you're on an oval. You're in the Olympics and you're whatever those things where you wear those really goofy helmets that make you look like alien and all that stuff. Do they ride like this? Because if they did, they'd crash a lot, wouldn't they? Because they're turning. No, how do they ride? They ride like this. I'm going around the circle. I would slide in that direction, but I'm accelerating in that direction. Where is my head looking as I'm moving around the circle? That way. In fact, it's not only simple physics, it's an absolute. You have to be looking in the direction of your acceleration. Because if you're not, then you have absolutely no control. And that's why I said when I was going down the Helix, people all the time get stuck because they drive with blinders on. Nobody drives a curve looking forward because you don't know where you're going to be next. They'll drive looking forward and they'll, oh shoot, I should have turned, and now they can't. There's not enough room, and they scrape their vehicle. I see this happen almost every time, and I've rented, I don't know how many times, 50 times. Yeah, I've never had an incident. So now let's go to the Helix. Okay, let's do the exact same thing. So my velocity vector, of course, just like before, I'm not even going to bother with the k. It's going to be negative sine t cos t1. So as I'm moving, I'm saying this when I'm going up. I could also be going down, because you have to go up the thing when you return the car, by the way. You go down when you rent it, but you got to go back up 7 flights to return it. And then my acceleration vector is the negative cos t, negative sine t, 0. Well, that's kind of interesting. This velocity vector has 1 unit in the z direction, which means the velocity vector is actually always pointed uphill. That's really not that hard to see, right? If you think of your tangents, aren't they always going to be pointing upwards? But this acceleration vector is completely on the xy plane. There's no z component. I'm going like this, but my acceleration is completely horizontal. So where's my acceleration at all times? Horizontal, directed at the z-axis. Because that would be the center of my circle. Remember I said you're on top of the z-axis, you close in one eye to make it 2-dimensional. You're looking down, you see a circle. And it turns out your acceleration is completely circular. Your acceleration is completely two-dimensional. Now, no one sees that one coming. Your velocity is three-dimensional, but your acceleration is only two-dimensional. There's no z component. So you're accelerating horizontally, which is why when you're accelerating, you look sideways. You don't look sideways up. You don't look sideways down. You look perfectly sideways. Now think about that for a moment. You're not moving sideways, but your acceleration is completely sideways. That's why your head turns towards the center. So if you ever find yourself in this position, when I'm driving, I literally am doing this the entire time I'm driving on that thing. My head is completely sideways, which is hard to do because you're doing 7 loops. You know, you kind of get a little stiff and you can't look away. Whatever you do, don't look away. So this is the simplest motion there is. Now, over the next few days, we're going to see this. All motion is either circular, linear, or somewhere in between. So what do you think most things are? Somewhere in between. If your motion is circular, then the acceleration is really, really easy. It's always the center of a circle. But if my motion is linear, then my acceleration is going to be in that same direction, isn't it? Because I'm not turning. It's in that direction. Okay? Linear is boring. Okay? Linear motion is boring. So as I'm moving through space, there's going to be circular moments. So what I want to point out, and this is not today's lecture, this is actually next day's lecture, but what we're going to see as we move through space, and I'll just do it two-dimensionally because that's easier. You know, I'm moving, and maybe I'm doing something crazy. I'm on a windy road. At every point on this curve, you can easily draw a tangent line. Do you agree? I mean, you could kind of eye shot it. But I'm not interested in tangent lines. I'm interested in tangent circles. At every point on here, there's a tangent circle. In some cases, it would be really big. In some cases, it would be really small. The tangent circle is the one we're looking for. That's next day's lecture. The tangent circle tells me everything I need to know about my acceleration and everything else. Because remember, I said this is not circular motion, but at every point on there, if I have a tangent circle, then the acceleration must automatically be pointed towards the center of that circle. That kind of cool? So we're going to go into great detail next day talking about this. It's the notion of what's called curvature. There's actually a numerical value that describes a curve. So I use windy roads as an example because all of us can conceptualize that. And the windy road doesn't have to be horizontal. The windy road can be going through the mountains, right? It doesn't have to be two-dimensional. Everything can be three-dimensional. A lot of times we're going to be doing three-dimensional things, but we might be just on the XY plane. See, we live in 3D, don't we? But everything we do right now, our motion is horizontal, isn't it? We're not going up or down when we move right now because the floor is flat. Does everybody follow that? But if I'm on outside in nature, I'm on a hill, I'm going up and down, it's a little different. I'm just throwing the stairs, right? Oh, okay, I can have vertical movement. But most of our motion here is going to only involve the x and the y because the z component right now is going to be a constant. It won't be 0. Why won't the z component be 0? What floor are we on? Yeah, that's why the z component's not 0. We're 40 feet, 50 feet in the air. So that would be our z component. But it would be a constant, and that's huge. So if I gave you a simple vector, that's easy. Now, in general, we like being able to describe things using functions. But a lot of times, it's at that point in time, what were you doing? If you're out on the road, right, and you're driving, maybe you're driving too fast, whatever, at that point in time, how fast were you going? You see, if you said, well, what was your average speed for the whole trip? That doesn't tell me anything, because you might have stopped several times. You know, you drive like a maniac, right? You drove 90 miles an hour the whole time, but you stopped several times, so your average speed was only 60. But at that moment in time, how fast were you going? I don't want a function, I want numbers. So a lot of times what we're going to do, let's start with something simple. I've got r of t, let's say, is 3 cosine 2t, 4t squared, e to the 3t. Let's just keep it simple, all right? I want you to find, v of 2. I want you to find a of, I don't know, a of 1. So that's how we would write it. So these would be vectors of scalars. There would be no functions in my answer. So there's an order of things, and this is not trivial. Think Calc 1 for a moment, okay? You had to take derivatives, you had to evaluate them in numbers. You did that kind of stuff all the time. So of course, the easiest way to do that is evaluate your function and then take the derivative. And you found calculus really easy. Because when you evaluated it and then took the derivative, the answer to every question that exists is what? Zero. God, calculus is so easy. And by the way, I've had calculus students do that. They evaluate, now they have a constant, and now they take the derivative. No, you have to take the derivative, then evaluate. And I say it sort of half jokingly because even in Calc 3, people are guilty of that sometimes. No, evaluation comes last, not first. So let's find v of t first. What's v of t? Negative 6 sine 2t. 8t.
3t.
3e to the 3t. And now let's find a of t. Okay? So what's a of t? So a of t would be negative 12 cosine of 2t, 8, 9 e to the 3t. Okay, not that exciting. Now the question is, what is v of 2? What is a of 2? So I just evaluate these at those, or I'm sorry, a of 1. I just evaluate these. No thought given, just so replace t with a 2. So what would that be? Negative 6 times the sine of 4, 16, 3e to the 16. Okay, that's it. It's not very exciting, but that's the direction I would slide. If this describes my motion, and I hit the banana peel right at 2 seconds, that's the direction I'll slide.
It would just be 3 to 6, right?
Did I? Oh, thank you. Yes. Thank you. Am I going in the right? Yes. And now what's a of 1? I do the same thing, but now I do it on this guy. So negative 12 times the cosine of 2, 8, and then 9e to the 3rd. Yeah, okay, I mean, don't read anything into the answer. That's just how we find the answer. It's actually that simple. Okay? Now, these will help me describe motion if I actually want to talk about, okay, here's how you were moving through space, and at that time, can you tell me the direction things were going? We are going to be able to break this down. When we actually describe the acceleration, there's pieces. There's a whole bunch of stuff going on that's way more than just this finished version. Okay? Remember I said all motion is circular, linear, or both. So what we're actually going to do is take the things that are not pure circles and not pure lines. Those are boring. Those are really not very interesting, and they're extremely easy to work with. So let's just take motion in general. Then at every point as I'm moving along a curve, there's a circular portion and a straight portion. And so I describe my motion by saying how much is in the circular, how much is in the straight. Think about that for a moment. Okay, that makes a little more sense. Now, what if it's purely circular? Well, then it's all circular and there's 0 in the straight. What if it's all straight? Then it's all straight and there's 0 in the circular. Most things are some combination of the two. Now think about that. So if you're moving, let's just say I'm jogging, okay? I'm jogging and Kenny over there, he decides to really crank up his gravitational pull today. So I'm running this way. He really turns on the gravity today. He has the ability to do that. Am I going to all of a sudden go towards Kenny? No. That's not possible. If that were the case, then all things would be flying towards the sun right now, right? The sun's got a lot of gravitational pull. No, what would happen is it would cause me to veer. It would cause me to turn. Because he's pulling me off my, what was a linear approach. I'm now curving. I'm not running towards him, but he's causing me to change and curve. So knowing how much acceleration I have tells me where I'm going to go. Remember, I'm running. If I slip, I'm going to slide linearly. But that doesn't tell me where my next step is going to be. Only my acceleration tells me my next step. Now, one of the things that's easy to calculate is if the acceleration, right, if there's only one thing involved, like in this case, like gravitational pull or something, that's easy. But we're talking horizontal, okay? Oh, vertical movement. That's a little bit trickier. So I'm going to give you an overly simplified situation here, just so we can do some simple calculations. This is not pure physics class, because if it was, we'd have to consider a lot of different things. All right? Now, in Calc 1, all right, we want to play catch in Calc 1. So what do we have to do? We have to stand in the same spot, and we throw the ball which direction? Straight up. That's what you did. Basically, algebra through Calc 2. Remember, you threw the ball in the air. And then when you drew the picture of the motion, people always forget where it came from. You did this in intermediate algebra. You did this in pre-calc. You probably did it in Calc 1. Time, distance. Maybe you started this high off the ground. You threw it up in the air. You guys remember doing stuff like this? Well, isn't that the motion? No. This is how high it was when I started. 1 second later, I'm this high. 2 seconds later, I'm this high. 3 seconds later, and eventually hits the ground. But I had to throw it straight up in the air. Or I was really high up in the air and I dropped it. Or I gave it an initial speed. Remember all of those different things? But you had to only go vertically. We have no mathematical way of describing motion this way until today. There's absolutely not possible in any context to describe, I'm going to throw something into Kenny. That's not possible until today. We're going to be able to do that. Because before it's straight up, straight down, and I'm plotting my distance over time. But it's still straight up and straight down. So what sort of questions did we have? What was the initial speed? How high off the ground did I start? How fast is it going when it hits the ground? Right, these are things that we did, and they were not difficult things. And so I want to remind you what we did. So we could use metric, we could use English standard, and so in physics we use metric. No, you don't. You use 9.8. Acceleration due to gravity. It's not 9.8. It doesn't stop. In fact, you're doing it right. What are you probably using? 9.81. That's far more accurate than 9.8. People say, well, I use metric, I use 9.8. Well, then you're not using metric because you're using a rounded off value for convenience. No, no, no. I'm not interested in that type of calculation. I want to use happy numbers. So in English standard, what do we usually use for acceleration due to gravity? What number? You know, it's because this is what you use all through calculus. You never use metric once in calculus. You always use English standard. 32 feet per second squared? Anybody use that? I'll show you why you know you always use it, because you always have the same coefficient in every single problem that you ever did. You went, oh, okay. But it's not 32 either. It's actually 32.18 if you're going to be accurate. But we use 32 because it makes the calculations really clean. And I'm not interested in ugly numbers. I'm interested in concept. Let's get the concept correct. So if I'm talking about the straight up and down, okay, because we're going to tweak this to 3D, we say it's what? Well, if acceleration due to gravity, okay, we're talking non-vectors for a moment. So we always use, we'll say acceleration due to gravity, we'll call it g. Whether you choose to use 9.81, whether you choose to use 32.2, doesn't make any difference. We'll just call it g. Then what's your speed? I have to integrate with respect to time. So that would be what? Gt. Now here's the thing. If g is just a constant, like 32 or 9.8, then technically it should be what? Negative. Whatever the number you have there, it has to be a negative number because acceleration has got to point downwards. That does matter. So I'd rather just say, let's call it negative g, where g is a positive number. Sometimes it's easier to conceptualize. So then this would be negative gt plus constant plus what?
T naught.
Well, or I'm sorry, that we'd call initial speed. Oh, I'm going to drop an object, my initial speed is 0. I'm going to throw an object up in the air. I have an initial speed that's positive. I'm in an airplane and I'm going to throw the object straight down. My initial speed is negative. Does that make sense? Those are the three options. Do nothing, throw it up, throw it down. If down is negative, throwing it down would mean I have negative. So this is what this is. So then if I integrate again, this would be negative 1/2 gt squared plus v0t plus s0. And this is the universal equation you used in remedial algebra. What coefficient did you see in every single problem that you ever did in remedial algebra? You always saw a negative 16. Think back. Every algebra problem ever written puts a negative 16 there. Every calculus book puts a negative 16 there. If it were metric, what would they be using?
4.9.
Negative 4.9. You go, oh yeah, and calculus always uses a negative 16, just to make the numbers easier. It's just easier to work with a 16 than a 4.9. Does it make it more or less correct? No. We're trying to get a concept down, right? Not do a problem that you have to use a calculator to get an answer. So this is the simple height equation when I'm going straight up and down. But here's the thing, right? I see Griffin over there. I want to throw you the ball. I'm going to throw it to Griffin. I don't want Griffin to stand here and go straight up and down. That's too boring. I want to throw it that way. So I have to be able to describe this motion. Now, this is three-dimensional motion, kind of, but not really. When I'm throwing it straight up in the air, it's one-dimensional, isn't it? I live in 3D, but really the motion's one-dimensional. I'm on the same line. So when I'm throwing to Griffin, we're on the same plane. That's not three-dimensional, other than I'm cutting, in 3D, I'm cutting this plane, but the motion, if you look at the rim, the motion is entirely on one plane. Now, I'm not talking about a strong gust of wind blowing sideways. No. No, I'm throwing the ball, we're on the same plane. So I need an X and a Y. This was only the Y, wasn't it? Everybody got that? This was only the Y. I need an X and a Y. Now, there are certain things that are going on that we tend to ignore. This is a crazy question, and I ask it every semester, and I'm always amazed. Has anyone here ever jumped out of an airplane? Okay, there's always somebody who's jumped out of an airplane. With or without a parachute? Oh, with a parachute. Okay, so you're not doing the whole Steve Rodgers thing. You get there faster without, by the way. So if you're jumping out of an airplane, you just keep going faster and faster and faster and faster and faster. Or at some point you stop speeding up. Huh. And what does the parachute do? Does that make you stop? No, but what does it do? It slows you down. Oh, so that you don't hit the ground going too fast. Now you've all seen the Bugs Bunny where the plane and right before it hits the ground stops. And there's two versions. One is they ran out of gas. That's one of my favorites. And the other one is they reached terminal velocity, which is arguably the stupidest term ever invented in the history of the world, because terminal velocity literally means you stopped. Terminal velocity means stop. When you run full speed into the wall, the moment you hit the wall, you've reached terminal velocity because you stopped. I'm pretty sure the plane didn't stop. It probably crashed. It's not terminal velocity. It's not even like terminal velocity, was it? Terminal acceleration, which, by the way, isn't even a similar in any conceivable way concept. You stopped speeding up at some point. Why?
Air resistance.
Air resistance. That's what the parachute does. It actually increases the air resistance. So at what point do you stop speeding up? When the force due to your air resistance is equal to the force due to gravity, you don't stop, you stop speeding up because you're actually subtracting in a sense. Now what does the parachute do? that really increases it. So the problem is, if you're going really, really, really fast, you're going to have to factor in air resistance. Okay? And where people get in trouble with this, I love Professor Newton. He was great. He taught me a lot of stuff, and he was, until that Apple thing hit him in the head, he was never quite the same. But people misquote and misunderstand his laws all the time. One of the most important laws that Newton has is two objects of equal mass must fall at the same rate. Pretty sure that doesn't happen anywhere on planet Earth unless you're in a vacuum. In other words, that law only applies in a vacuum. How often do you guys hang out in vacuums? How many have their own spacesuit at home? So, you know, we're going to do the vacuum thing later on. Not very realistic, is it? In other words, I just created a situation where I had two objects of equal mass, but not equal force. Not equal what? Surface area. Beautiful. These do not have equal surface area. Surface area has a lot to do with acceleration because the surface area. So, Griffin, you jumped out of a plane. What happens if you ball up?
Go faster.
A little faster. What happens if you spread yourself out? Why? You didn't change mass. What did you change? Your surface area, the exposure. Okay, and again, that's the parachute thing. So what we're going to do is we're going to play catch in a vacuum. I have some spacesuits out there so we can all play catch in the same vacuum. Because if we play catch in the vacuum, then we can ignore air resistance. If we don't, then you actually have to factor that in. What about things like wind? You got to factor that in, which now makes what we're talking about so much more complicated. We can't even do the problem anymore. There's way too much going on. I'm going to throw you the ball and a bird gets in the way. Right? There's too many factors if we're just out in the world, because if I throw it fast enough, oh, by the way, what is it I'm throwing? The air resistance of just going sideways if I'm throwing something that's large. So I like to think of it this way. We have an object, could be a ball, you know, could be a rock, whatever, but it's not huge, so not a huge surface area, and I'm not throwing it so fast that I actually really even have to consider air resistance. Anybody ever watch football or baseball? Are they throwing things pretty fast? Baseball, they're throwing things really fast. Football, you know, that quarterback's throwing, it's going really fast. But it's not in the air for very long, and it's not going so fast that air resistance is going to change it a lot. Wind might have an effect. But what if they're playing in a domed stadium where there's no wind? Now you can say air resistance is negligible. So I want to do a really simple problem where we're going to ignore air resistance because we're playing in a vacuum. Everybody okay with that? And we're going to use English standard units because then it makes the number crunching just way simpler because we're trying to get a point across. Well, I'm going to do everything metric because that's all we ever do in real life. Really? In your day-to-day life you do everything metric? If I asked you how tall you were, I doubt anybody in this room could give me the correct answer in centimeters or millimeters. You'd have to convert. You probably. Okay. Yeah. One. And if I ask you how heavy you are, all of you are going to give me the wrong answer. Because I'm still waiting for the first human being in my entire lifetime to give me a metric answer for weight. How do I know that there's no possibility anybody's ever going to give me a metric answer for weight? Because I bet none of you have any idea how heavy you are in newtons. Oh, kilograms is not weight. If I asked you how heavy you are, kilograms would be the equivalent of you giving me your age when I ask you how heavy you are. In other words, it's a completely different unit that's not even similar. Speed and acceleration are at least a little closer together. They both involve distance and times, different exponents on the time. But mass isn't weight. Mass is a scalar. Weight technically is a vector. They're not even similar concepts. But people say, well, I'll give you my weight in kilograms. No, you're going to give me your mass in kilograms. That's not the same thing. It's actually quite different. And in calculation, it doesn't work particularly well. No, so we'll use English standard because then you can give me an answer that's easier to work with. So how do we do this in English standard? I always have fun with the whole metric thing because people who were born in a different country are used to using metric and they still give the wrong answer for weight. Because kilograms is not weight, newtons is weight. And if I'm using kilograms, then I'm also not using the correct multiple. So I'm going to get answers that don't really work too well. So here's what we're going to do. I'm going to throw a ball, and wherever I throw the ball, I'm going to call this 0. See, if I called the wall 0, and I'm 10 feet in front of the wall, then I'm 10 feet from the wall, and I've got to kind of work that into my equation. Why don't I just, wherever I am, I'll call that 0. Does that make more sense? I don't want 0 to be some other starting point. So where I am, I'm going to be here. Now, this is one thing that cracks me up in all the calculus books. They give incorrect formulas for what we're about to do because they're really simple formulas. They'll say your initial height is always 0. So when I throw the ball to Griffin, my initial height of releasing the ball is 0. Well, I guess if I dug a hole, I'm 5'9", I'd probably, so let me dig a hole about 6 feet deep. And then when I let go of the ball, I guess I could be letting go of the ball right at about a height of 0. Would that work? And now I can say my initial height is 0. Or would that be absurd in basically every conceivable context? Yeah, your initial height can't be 0. That'd pretty much be impossible. Well, what if I'm launching it off the ground? You guys ever see the space launches? It's not touching the ground. It's way off the ground when it starts because it has to have room. Yeah, your initial height can't be 0 ever. But all the calculus books do that because it makes the formulas really, really simple. Impossible, but simple. Now, let's say you're, S0 off the ground. How's that? And now I'm actually going to throw it to you. I want to describe this vector. I need an R of t. So make a little box here. When I throw the ball, now when we threw it straight up, that was easy. When we threw it straight down, that's easy. I'm going to throw the ball with an initial speed, but there's also going to be an angle made with the horizontal, isn't there? Everybody understand that? There's an angle, and I have to take into account this angle. Let's call this angle theta. There's an angle made with the horizontal that, unless I'm throwing it vertical, I'm going to have some in that direction, I'm going to have some in that direction. Agreed? So the original S of t that I used won't exactly work. So how much is going in the horizontal? If S of 0 is my start and V of 0 is my initial speed, how much is going horizontal? I think it's a SOHCAHTOA.
D cosine theta.
It's going to get cosine theta. So it's going to be V0 times the cos theta. Okay? T. Why t? Because V0 is distance per time. And then I got to multiply it by how long. Oh, so when time is 0, I haven't moved horizontally yet. But after 1 second, 2 seconds, 3 seconds, and so on. Okay? What is y of t? Well, it's the same equation we just did a moment ago. It's -1/2 gt squared plus V0 t plus S0. I'm leaving a space here because I'm not throwing it straight up. Oh, I don't get all of it. I get SOHCAHTOA. I get sine t. I'm sorry, sine theta. This is the only difference. The vertical we just did a moment ago, S of t looked almost identical. There was just no sine of t here. But now I have to consider sine of t because I'm not throwing it straight up. I'm throwing it at an angle. What if I actually, as hard as I threw it, I could throw it perfectly sideways? Then it's going to go like that. Do you agree? If I threw it perfectly sideways, then this term would actually be 0, wouldn't it? Because there's no upwards. Not if I threw it sideways. Now this is one of these things that kind of defies, for a lot of folks, it defies common logic. I'm standing on the edge of a cliff, really far cliff. And Griffin's on the other side, and I want to see how strong my arm is. I'm going to try to throw it to Griffin. Well, obviously it's not going to get you. It's going to fall. Obviously. Tell me about my horizontal speed.
It's constant.
It's constant. What about my vertical speed?
It's vertical.
It's increasing because of gravity. But my horizontal speed is constant forever. Short of hitting a bird, a strong gust of wind or something, a lot of folks don't think about that. They think gravity is affecting the horizontal. No, gravity has no effect on the horizontal. Gravity only affects the vertical motion. So when I throw that rock, I'm on the end of the cliff, and I throw that rock with a particular initial starting speed, whenever it hits the other side, the horizontal speed was exactly what I let go at. But remember, it's falling, so it's speeding up because of the gravity, but not horizontally. Does that kind of defy logic at first? You think, but shouldn't gravity affect horizontal? No, gravity. When you're running in a race, you're not feeling gravity. You're running sideways. feel gravity when you're falling, but not when you're running sideways. So the position vector is simply this. Now, we're playing in a vacuum, like I said, so we're ignoring air resistance. Everything's always going to be given to you. And just to make life easier in this context, I like using the 32, not 32.18 by the way, just because it makes the number crunching just really clean. You know, it doesn't matter how ugly the problem is, it ends up not usually being that terrible. So let me come up with a really simple problem, all right? Give me just 1 second. All right, let's say you throw a rock from a height of 192 feet. That means think that you're standing on a tower, if you want. That makes it easier, right? And you're throwing a rock from a height of 192 feet at an angle of 30 degrees, that's with the horizontal. We always measure the angle against the ground, not against the vertical. That would be kind of confusing. With initial speed of, let's say, 128 feet per second. That's really fast. You got a really strong arm. Okay. What sort of questions can we ask? Well, first question is let's describe the motion. So that's basically find R of t. Can't answer any questions until I got the R of t. Okay. Now, what sort of things can we? Do you agree that it's eventually going to hit the ground? Okay. So how far away does it hit the ground? Now, this is not an ambiguous statement, but a lot of people make this harder than it has to be. If I'm standing here and I throw as far as I can. I'm in the Olympics, I started off as a javelin catcher, and then I found out it was easier to be the javelin thrower. Yeah, it's a little safer. So I'm throwing the javelin, I'm throwing the discus, I'm throwing something, and they measure how far I threw it. Do they measure the arc it travels in the air? No. What do they measure? How far away on the ground did it land? From my feet, not from my hand. You always measure, when you say how far away, it's from where I'm standing on the ground to where it's touching the ground. Having said that, I have people, no, I measured it has to be the arc length. Really? So if you're flying, let's say Portland's about 900 miles away. So you're flying to Portland. So how far did you fly? Well, let me get out and measure how far the plane traveled because it went up and it came. No. Horizontal distance is ground to ground distance. There's zero height in the calculation. You're making it too complicated. Because otherwise I have to factor in the fact that I let go of it off the ground, don't I? No, just on the ground to on the ground. So how far away did it travel is the horizontal distance from my starting point to where it landed. That's it. That's easy. That's never complicated. So how far away does it hit the ground? What else? Can I ask how high it reaches? Sure, I can ask that question. I'm less concerned with that one. I'm more concerned with maybe, let's say it this way. Speed on impact. Now, I throw something at a certain speed. And remember, we're measuring the speed when it leaves my hand, so we're already factoring in the angles, vertical and horizontal. But I'm throwing it at a certain speed. When it hits the ground, should it be moving slower, faster, or exactly the same?
Faster.
Why faster? Yeah, even though I'm standing on the ground those few feet, it might be tenths. I'm launching this thing from a high tower. Now, if we're in a vacuum, I'm launching from a high tower. When this object is at exactly the same height on its way down, how fast is it going? In a vacuum, exactly the same speed. Exactly. When it's above this, is it going slower or faster?
Slower.
Yeah, because literally it's stopped at this moment, right? It's starting to come down. Oh, and it's speeding up because of gravity. So when you ask for impact speed, it can't be slower than your initial speed. If it is, that means we got an error somewhere. That's kind of a simple check. If I'm letting go at 128 feet per second, it should be going a little faster when it hits the ground. How much faster? I don't know. Probably not like 10,000. It's only falling 192 feet. But it's probably going to be a little more. How much more? I don't know. But it ought to be a little more. Do you agree? That's a simple check. Okay? So these are nice questions. So let's do this problem. So using 32 feet per second squared for the gravity, just because again it makes the numbers easier. Let's do each one separately. What is x of t? Well, it would be what? It'd be 128 times the cosine of 30 degrees t. What's cosine 30? I use 30 because it's a nice symbol. Pretty much you're only, in textbooks, they'll only use 30, 45, and 60, just so you know. Just because it makes it a lot easier to work with. What's cosine of 30? Root 3 over 2, so this would be 64 root 3 t. Okay? What's y of t? That would be negative 16 t squared, because I said we're going to use 32. So 1/2 g. Plus 128 sine 30 degrees t plus 192. What's the sine of 30 degrees? 1/2. I love using 30 degrees for exactly that reason. So this would just be 64t plus 192. First, okay, that's first. So find R of t. All right, so there's my first thing. There's my R of t. Next question is, how far away does it hit the ground? What do I need before I can answer that question? I need the time it takes to hit the ground. I can't just randomly make up a time. Oh, it hits the ground when the height is 0. So how do I find that? Set y of t equal to 0 and solve. And because it's only going to be a quadratic, that's generally not going to be a challenging thing. So the second question means I need to do this. 16t squared plus 64t plus 192. I need to figure out at what time that is 0. I can certainly use a calculator, I can use my quadratic formula, or I can notice they're all multiples of 16, so I can factor it. That'd be easier. Does that factor? T minus 6t plus 2. More technology for this one. So this is going to be 0 when t is 6, or when t is negative 2. What do you think about it? The solution to this equation is t equals 6 or t equals negative 2. Negative 2. I hit the ground 2 seconds ago? No, that's extraneous. Extraneous happens all the time. Extraneous means it solved the equation, but it can't answer the question because I can't have negative time in this context. You didn't do anything wrong. You got a quadratic. You're supposed to get 2 solutions. Oh, okay. So I kind of have to go with the positive one. So what does this mean in simple English? I'm going to hit the ground in 6 seconds. Okay? So question number 2 is, what is x of 6? That's how far it traveled horizontally in 6 seconds. And so I just simply put a 6 in there. What is 6 times 64? 384. So it's 384 root 3. Are there units? Feet in this case. Yeah, units are important because sometimes we're asking speed, sometimes we're asking distance. Now, I'm pretty happy with that answer. And of course, all of you, that makes perfect sense in your head. You know exactly how far away 64 root, or 384 root 3 is. I'm going down to Home Depot later on today, and I'm going to tell I need 384 root 3 feet of lumber. So they're going to look on their, their big thing where they mark, and of course they have a root 3 on there. That is the answer. I don't know how big that is, though. This would be a really good time to maybe pull out the calculator. In other words, that is the answer. But I'm saying how far away, and I don't know what that is in my head as a value. Like I said, when I go to Home Depot, they're not really going to be able to help me. So that's approximately what? About 665.1. This is the answer. But in actuality, which one's probably more useful? 665. Probably the second one, because now, okay, it's about 665 feet away. By the way, you can't get the second one without the first one, so to do it, you don't have to do that. But I would kind of like having a feeling in my head, because what if I had some outrageously large root and I have a number, I have no idea, and it turned out, it was 1,000,000 feet away. And you go, you know what, that might be a little big. This is also a way of checking, saying, does that answer make sense? Yeah, I'm really high up in there. I threw this thing really fast and it landed over 600 feet away. Really fast. I mean, you probably couldn't throw it that fast. That's really fast. Okay. Let's see what. Yeah, we have the 6. I can erase this. So the last question was impact speed. Well, I can't tell you the impact speed without the velocity vector. So we need to find the velocity vector first. So what is v of t? So there it is. So I want to take the derivative of this vector. So v of t is 64 root 3 plus 64. Now, do you notice something about my velocity vector? The x component is a constant. Isn't that what we just said a moment ago? Oh, yeah. Horizontal motion has to be constant speed. But the vertical is changing. In fact, when I first release it for small values of t, this is still going up, isn't it? But for large values of t, this is going to be going down. Agreed? So when does it hit the ground? When? In 6 seconds. So what we need to do is we need to find the magnitude of v of 6. Any other time will be useless because that's not the time it takes to hit the ground. I only want the speed when it hits the ground, not just before it hits the ground, not a second after it leaves my hand. So what is v of 6? Will be 64 root 3 negative 128. And that negative is actually quite important because that means it's, by the way, if that second component was positive, what does that mean? This going up and eventually leaving the atmosphere. You all understand, I'm not joking. If they're both positive, then it's going up. Right? Remember, this is the direction you slide on the banana peel. They both can't be positive if it's going to hit the ground. This one's got to be negative. It's coming back to Earth. So now, you have your calculator. So v of 6 is going to be that squared plus that squared. And that'll be a nice happy integer value, by the way. All right, so what do you get under the root? Square root of... how many have a calculator that actually will reduce roots for you automatically? I love those calculators. I don't have that calculator. I love those calculators. Oh my gosh. Otherwise, I sit there, you know what I do? I said, no, let me take that divided by 16, then I'll divide by 16, then I'll whittle it down. It'll take me like 15 seconds, but I like the calculator that just tells me, oh, by the way, rather than whittle it down, I would say, I used to teach remedial algebra. And I would give them a really large number under the square root, and I'd say, let's go ahead and reduce this. You don't have to do this, but I do stuff like this. All right, 4,096. And they'd be really clever and okay, that's root 4 times root 1,024, and then it's root 4, and then it's root 4, and it's 256. And they do this for a couple minutes, and then eventually they got the answer was 64. In other words, 4,096 is a perfect square. And then after they got done, I'd say, you know, before you do all the algebra to simplify it, why don't you check to see if it's a perfect square? Then you could be done in like 1 second. And can you do that? So before I start worrying about producing that, is that a perfect square? Nope. Okay, now let's keep going. Sometimes, very rare, but sometimes you may actually get a perfect square right there, in which case you're done. So we don't have to sit there and manipulate our calculators, because if you don't have a calculator that reduced it, you're playing with your calculator. What does this reduce to?
64 times root 7.
64 root 7. And what are the units?
Feet per second.
Feet per second. Now, that's a perfect answer. And once again, I have no idea how big that is. That is the answer. But this is a very appropriate time to do a decimal approximation. In fact, this is the time you really have to. Is it possible that this answer is wrong? Is it possible? Is it possible we made a mistake? You messed up somewhere along the line. So, of course, it's always possible. And I really would have no way of knowing that. Okay? Give me a decimal value here. It's about what?
169.33.
It's about 169.3 feet per second. Now I have a really good feel. Are you happy with this answer? You don't know, you could have made a mistake, but really the thing is, if you'd made a mistake, you're probably not going to have an answer that's this viable. Did I speed up? Outrageously? No, but I sped up. If I don't do this, is it possible, particularly, I made a mistake, is it possible that this could have actually be lower than that number over there? If I made a mistake, it's possible, and I would never know. That's the reason you need to calculate that. You need to know, yeah, it did speed up. Yeah, by the way, giving me this as an answer is absolutely correct. But you got to do this to at least be able to check it versus that number. Yes?
Do you want us to put both on a quiz example?
Well, the answer is, I mean, technically the answer is this.
Yeah.
You're reducing, I don't, if you can do this, that's great. But if you don't have a calculator that does this, you got this, but you don't, come on, nobody has a feel of how big this number is. So do this so that you know. This is the answer, this is an approximation of the answer. You never give the approximation without giving the actual numbers that you did. I'm saying putting them both is wise, because the second one kind of confirms to, yes, I did it right. If I leave it as a root, it's correct. But again, I don't know if any of you can actually figure that out in your head, how big that root was, because it's too big. So a problem like this, all the pieces of the puzzle should make sense. I tend to, give you problems that are, the numbers kind of come out nice. But understand that all your answers probably have roots in them. Okay? It would be extremely difficult for me to engineer a problem where there were no roots in the answer. That's kind of hard to do. Because no matter what angle I chose, are there any angles where sine and cosine are both rational? No. Not even going to bother wasting time. There's no angle that exists where both sine and cosine would be rational. In fact, there aren't that many where either one of them are rational. Here's one of them, right? Sine was rational, cosine was not. At 60 degrees, cosine was rational and sine was not. But there's no angle of trajectory between 0 and 90 degrees where they'd both be rational. Usually they'd both be irrational. That's why I tend to use nicer numbers like this. Now, simple question. What should be the angle? By the way, there's another name for the 30 degrees. Do you ever know what we call this? In trig, you use this term all the time. It's called the angle of elevation. You guys remember that term? It's the angle of elevation. Angle of elevation is always measured against the horizontal. What angle of elevation would maximize my horizontal distance? 45 degrees. Now, that's not always common sense. You would actually have to do a little bit of calculus, but it's actually 45 degrees. If it's too steep, I'm going to go higher and higher and higher, but I'm not going to travel horizontally. But then why not make it lower? Because it's going to hit the ground too soon. So you're not getting high enough off the ground. 45. Now, I love using that as an example. Who here knows who Aaron Rodgers is? Quarterback of the Green Bay Packers. He has an artificial arm, kind of like Bucky Barnes in Captain America. He's got, because he can throw a football from one stadium to another stadium. I think he can actually do it from one city to another city. It's uncanny how far he can throw a football. So if you ever watch at the end of a game, his team might be trailing, and they've got the ball, and they're really, 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 really far away from the goal line, and he'll drop back, and he'll throw the ball. It'll leave the atmosphere for a moment, and it'll come back down. It's called a Hail Mary. How many have ever watched him throw a Hail Mary? I've never seen an object thrown that far in my life. It's uncanny how far he throws it. But he doesn't throw it at 45 degrees. He'll throw it probably more like a 60-degree angle. Huh. Some people will do that and they'll throw it at a flatter angle and the ball won't reach the end zone. Aaron Rodgers doesn't throw at 45 because he already knows he can reach the end zone easily. Why does he throw it at such an extreme angle this way? Does anybody know?
More time there.
So it's in the air longer before it hits the ground to allow all of his team to get downfield, and it's worked for him more than anybody in the history of football. It works because he can throw the ball so far already that he doesn't try to maximize the distance. He tries to maximize the time in the air. Well, maximizing the time in the air would be just throwing it vertically, wouldn't it? But that wouldn't really accomplish your goal of getting it. So he throws it at a ridiculous angle, way up in the air, and then when it comes down, everybody's waiting for it, and then they can jump. It's an interesting concept. So if you watch football, which you should, of course, if you watch the angle when a quarterback throws the ball, the angle is always changing. And I mean, I'm talking about the angle of elevation. See, if I'm throwing it a short ways, do I want a big angle? No, because I want it to get to you really, really quickly, and I have enough strength in my arm to get there. But if I'm throwing it further downfield, I need more of an angle, because again, I want it in the air longer. And if I'm just letting it go as far as I can, again, probably 45 degrees, but most throws are much less than 45 degrees. Why? If you're a football fan, why don't you want the ball in the air a long time?
Because it gives the defense less time to react.
Well, if it's in the air for a long time, then the defense has time to get to the ball also, and that kind of defeats your purpose. Everybody cool with that? Okay, let's do a couple more of these problems. This is actually one of the simplest things we're going to do, just because there's nothing about this problem that's tricky. So let's do a similar problem. Let me make up new numbers. I'll keep the 30 degrees just because it works so nicely. Let's see, hold on a minute. I'm not throwing this, now I'm actually shooting it out of a gun, What if the question was given in miles per hour instead of feet per second? Could you work good with miles per hour? Well, what would be the biggest problem of giving you miles per hour? It could be kilometers per hour. What's the biggest problem with that?
The unit for acceleration and gravity.
Yeah, acceleration due to gravity is usually in the seconds. Ooh. So if you were given miles per hour, you really couldn't work with it. You'd have to convert it to feet per second. There's actually a really simple conversion. I only show this usually in lower level math classes, but we talk about things, for example, when we're talking about the acceleration, we're talking about acceleration due to gravity, we're using feet per second squared or meters per second squared. So miles per hour or kilometers per hour isn't an entirely useful unit, is it? Now, another reason is feet per second squared. Miles per hour, we're using different units for both length and for time. Meters per second squared, kilometers per hour, same thing. So if I'm giving you normal speed, because that's how we talk in miles per hour, right? How fast is your car going? I don't think anybody's going to give me feet per second. I'm not a baseball fan, but I know, pitchers can throw a ball really fast. When they talk about how fast a pitcher throws, they always talk about it in feet per second, don't they? Or do they always talk about it in miles per hour? No. What's the irony of talking about how fast a pitcher throws a ball in miles per hour? They're only throwing it 60 feet. Do you see the irony there of giving you miles per hour when it's only 60 feet? Again, that's like talking about Usain Bolt. How fast is he running in miles per hour or kilometers per hour when he's only running 100 meters? It does seem kind of overkill because you're using completely different units. We'll do this problem in a moment. I'm going to show you something really simple. A lot of people don't realize how easy the conversion actually is. All right? You have miles per hour. You want feet per second. I could start with feet per second. You want miles per hour. How do you do it? It's actually really simple, and there's a really simple constant. Okay? Only 2/15. That's what this reduces to. So 1 mile per hour is 22/15 feet per second. 1 foot per second is 20 seconds miles per hour. Do you find that to be remotely useful? Almost an easier, really quick and dirty way. 22/15 is really close to 1.5. Really close to 1.5. So if I'm going 100 miles per hour, then I'm going roughly close to 150 feet per second. 15 over 22 is really close to 2/3. So when I said nobody could throw a ball this fast, that's almost 200 miles per hour. That's what I'm saying, nobody could throw a ball that fast. But do you find that could be useful? So if I gave you miles per hour and I asked the same question, you could easily convert it to feet per second. Kilometers per hour would be a similar notion. In fact, it might even be an easier calculation because it's 1,000 versus 5,280 as your constant. So this is just interesting, can be useful. I don't care if you remember this, but isn't that nice that it reduced so nicely? That's it, 22/15. Okay, so let's do this problem. Same 3 questions. I want you to do this on your own for a minute, and then we'll come back and we'll explore the answers. Some of this, because we're going to do this all over again. So I want basically the same 3 questions. There's sort of an order of things that you want to do just to make your life easier. Don't try to answer the question as your first step. Do it in pieces. Take baby steps. So the first thing I have is, what is my exit T? Okay. And then what is my Y? Now, because I used a nice happy angle, our numbers are actually fairly happy numbers. So what is the first one? And that would be time, and this one, negative 16t squared plus what?
144T.
Just 144t plus 576. Now, there are some absolutes in math and science that have never changed. They weren't important before technology because they didn't have the ability to calculate things, but since technology, there are some absolutes that a lot of people ignore and they don't understand. In any problem, what is the only thing you can ever approximate in any problem? The final answer. At no point along the way do you ever approximate anything, and the one thing you absolutely can't in any context, you cannot ever approximate a coefficient. If you approximate a coefficient, then every calculation you ever do will be incorrect. It'll be close. You don't, if your coefficient was a pi, you don't approximate pi, you have pi. You do your calculation and round that off if you want. And the reason I'm pointing that out is a lot of people calculate the root 3 and then use this for the rest of the problem. That's incorrect. And nobody in your chemistry or physics ever would accept a calculated coefficient, only a calculated answer. This is not the answer. X of t is 144 root 3 multiplied by whatever time I put in. I can approximate that result. You do not approximate this. This is a coefficient. A coefficient is not the answer. The answer is what you get after you do the calculation. And I remind people of that because sometimes we have really bad habits. Pi r squared is the area of a circle. Well, I'm going to just go ahead and approximate the pi, and then I'll do my calculations. Well, it really wouldn't work so well, would it? No, do your calculations and then approximate your answer if you wanted. So r of t, which is the most important part of this problem by a lot, is simply this: don't lose the t, and I have negative 16t squared plus 144t plus 576. All right. So the first question was, how far away did it land? So of course I need to find the time. You can always use your quadratic formula, but those numbers are real big. It's correct, but those numbers are really big. So I need to figure out when y of t is 0. Does that factor? It does? What is your final factored form?
T minus 12 over T plus 33.
T minus 12, t plus 3? Dude, how did I do that? Gosh. Does it work like that in general? If this were physics, is there any possibility time would be an integer value?
Probably not.
No, in fact, not only would that be impossible, you did it wrong if it was. But this is math. So we like it when t is an integer value. I don't say that jokingly. Measurements cannot be integers. That actually is impossible. A measurement has an infinite number of decimals. You can round things off, but a measurement cannot be an integer value. That would mean a 1 out of infinity possibility. Remember, measurements always have an infinite number of decimals. You would report maybe an integer answer. But this says, no, exactly 16, or excuse me, exactly 12. In real life, it's probably not that clean, but this isn't real life, this is artificial. Like I said, we're also playing catch, remember, in a really large vacuum. So if that isn't a little bit artificial, I don't know what is. Okay, so you're wearing a spacesuit. So t is 12, and I'll put it this time, we didn't do it last time. T does have units, it's seconds, because I don't want you putting feet. Pounds, I don't know, put some silly unit there. So, next question is, what is x of 12? So what's 144 times 12? So is that what we get? That's really far, I think. How far is that?
2,992.9.
I'm sorry, say
2,992.
2992.
0.98 feet.
0.9. Is that really far? almost 3,000 feet away. I am really high off the ground, and like I said, this is close to 200 miles per hour. So is that reasonable? Yeah, that's roughly 196 miles per hour. That's really fast. And I'm really high off the ground. So 3,000 feet away sounds really, really far, but considering how high I was and how fast it was moving, it's reasonable. I have no reason to disbelieve it, in other words. All right? What is V of t? There it is. So V of t is we're differentiating this guy.
44 root 3. And then negative 32 t plus 144.
Plus 144. At first, it seems like our vectors should be in R3 because we're throwing in 3 dimensions. But like I said before, when I'm throwing it from me to you, the path of the arc lives on a plane. It doesn't have 3 things. It's on the same plane. Now, if a wind is blowing, or I throw a big curve, that's possible. I'm throwing a frisbee, that's different. But we're talking about a path that's entirely on one plane. So therefore, if I now make my XY plane this way, you see, then I don't need a third variable. Because in a sense, there's nothing coming out of the board at us. So finally, V of 12 is, what's the second value? Negative
240.
240. Oh, I said 24. Did everybody get that? So now let's do this. This is probably going to be a really large number under the root. So 119,000. Now there's a really simple trick if you want to factor this quickly and not do it the old-fashioned way. Try 16s and try 9s and try 36s. To me, it's an easier way. I'm lazier than all of you put together. I take great pride in that because I like doing. I use a calculator. I use a calculator for roots. More often than not, I have the number before you guys have entered your calculator because my brain just computes easily. I look at this and I go, what's the easiest way out? Is this a true statement, what I just wrote? Is that true? 3 root 3 when I square it is 27. 5 when I square it is 25, so that's 52. Here's what I do know, without doing any work whatsoever. Can you always do this? Yeah. Should you always do this? Yeah. What if those were variables involved? Yeah, factor them out before you square. You can do this in every vector that exists. You can factor out a common factor before you square it, and that will be the coefficient that you factored out of your root. Now, root 52 is root 4, root 13. So I can go one more step, can't I? Didn't need a calculator to do that. Now, the reason I'm pointing that out is most of you don't have calculators that will do that quickly. In which case, this is totally okay. Now, I have a better feel, but I still don't know how big that number is. So after all said and done, what is this approximately?
346.1.
346.1 with units of feet per second. Is that number reasonable? I started at 288 feet per second. It increased, but it wasn't an outrageous increase, but it was definitely an increase. The reason I'm comfortable with that answer is if it were wrong, I just don't think it would be that good, that close, that reasonable. We were expecting an increase, but we're not expecting like multiples, like it's going 3 times as fast kind of thing. Am I right there? It's almost any answer that was more I feel comfortable with, unless it was absurd. if this answer was 10 times the original answer, you go, it's not in the air that long. It's probably not going to increase that much. Okay? Any question on any part of this? This is not supposed to be difficult. This just gives us a use of the vectors that we are doing. So if you don't get anything else, given any position vector, can you tell me the velocity and acceleration? Yeah, that's about the easiest thing you're going to do the rest of the semester. You're doing really simple derivatives. Now I have a simple motion problem where gravity, is affecting the problem in a vacuum, so we keep it simple. I don't have to worry about air resistance and things like that. There's no jetpack on the ball. There's no external force acting on it. Who does that? Yeah, in differential equations, we do stuff like that. Right? We make this problem really complicated in other classes. But right now, we're just trying to get a mental picture, and then we're moving on. We don't spend any more time on this. The next 2 classes are both huge. We are going to develop a lot of formulas in the next 2 classes. And I mentioned last day about having direct and indirect ways of doing every problem, because the formulas that we develop, some of them are kind of complicated, or if they're not complicated, their use can be complicated. Because taking derivatives of vectors that have been made into unit vectors can be really nasty. But we're going to do a lot of this. So as we develop formulas, I'm going to give you constant alternate routes. The other thing is, in the next 2 days, there will be times, like I did with cross product, where I'm going to bring stuff up, pre-printed notes, so that you can walk through and understand them without having to sit there and take notes. Taking notes is critical. You have to take notes. But sometimes in the derivations can be really long, and there's so much going on that you get lost in writing everything down. You kind of miss the point of what it is you're finding. So sometimes I will use the pre-printed notes and then just walk you through it. And so I will remind you, they will be, I think they may already be online. If not, they'll be online over the weekend. I will remind you, hey, you may want to actually print some of these. Then rather than taking notes in your notebook, you can write on the notes themselves and say, we did this because. You see, taking notes is not taking a picture of the board. I have people do this in every class. They will take a snapshot of the board. I already know how they're going to do in the class. They're not going to pass. They took a picture of the board. That's like watching the beginning, the middle, and the end of a movie simultaneously. There's a development. In fact, if you're a good note taker, your notes should be significantly more than I wrote. Because you're saying, we did this because. I'm doing this and I'm explaining, but you're saying, we did this because. This came from here, we did this. If you're just simply taking a snapshot of the board, there's no development. So all you're doing is writing results, but not explaining why and where the results came from. That's what notes are. Notes are understanding the development. Again, does it help you in any way to know this is the answer without everything to the left? No. It's everything to the left of this. This is just frosting on the cake at this point. But it was the development to get here. If I don't know the stuff getting here, then this doesn't mean anything to me. So a lot of times, again, I will give you pre-printed notes because the taking of the notes can be long and tedious. You remember the cross product. That was long and tedious. That's a lot of information there. The development was huge, but in that case, it was the end results. What we're doing next is actually the development, because we developed several things in similar ways, and then you can actually understand that. Then we're done with vectors until the end of the course. We have 2 more days of using vectors, and then we don't come back to vectors until the very end, the last couple weeks of the course. Okay? After that, we get into derivatives and integrals, and that's sort of the middle 2/3 in a sense. So motion is the big thing, and all the small pieces of motion that we're going to develop. The next 2 days, like I said, are huge from a formula standpoint, not from a calculus standpoint. Calculus is not challenging. It's what the heck did we say that's the important part. When I describe motion, there's a lot of pieces of the puzzle. There are several different things that go into this that we haven't seen yet that help us describe the motion. Okay? Any questions? All right, go ahead and stop recording and do the roll thing.